Hi everyone. In this video, we will continue our discussion of sequences of functions by today looking at both pointwise and uniform convergence of sequences of functions. We'll make use of a few of the examples we saw last time while also looking at new examples. And this will be just the beginning of our discussion as we will continue to look at the consequences of both pointwise and uniform convergence. So to begin, I want to first define pointwise convergence of a sequence of functions. We say a sequence of functions, f sub n, converges pointwise on a set A, which is a subset of the domain, to a function f, if and only if, for each fixed value A in the set capital A, the sequence f sub n of A, which is a sequence of constants, converges. So said another way, what we're looking at is we're looking at a sequence of functions. The sequences of functions each must be defined on a common domain D. And we want to define what we mean for that sequence of functions to converge to some other function f on at least some subset of that common domain, right? Sometimes we may be looking at the whole domain, other times we might only be looking at a subset of the domain, but we want to define what it means for this sequence of functions to converge on some set to a function f. And essentially what we're doing for this pointwise convergence is we're saying, well, go through and for each value A in the set, capital A, just plug that A into your sequence of functions. So if we go back to, for example, the sequence of functions f sub n of x is equal to x to the n, which we're going to look at more in depth here momentarily. But the idea would be if you want to show that it converges pointwise on, say, the closed interval 0, 1, you start plugging in values. So you say, well, what happens, right? What if I plug in 1/2? Okay. Now notice that by plugging 1/2 into this sequence of functions, what I get is a sequence of real numbers. I can talk about what happens to a sequence of real numbers. I have a definition for what it means for a sequence of real numbers to converge. Okay, so if I look at this, right, this will converge, that sequence would converge to 0. And then I could repeat this, right, for, pi over 713, right? And I would see that if I plug pi over 713 into this function, it'll converge to 0. If I plug in 1, right, this will give me the sequence 1 to the n, which is just the constant sequence 1, that converges to 1. Right? But the idea of pointwise convergence is I converge pointwise on this set A if for each A value I plug in. So every time I plug in a different A value, that results in a sequence of real numbers. And if for every A value, when I plug it in and form that sequence of real numbers, that sequence of real numbers converges, then I will say that my function f my sequence of functions f sub n converges to my function f, where that function f is just the function that at 1/2 has value 0. At pi over 713, it has value 0. At 1, it has value 1, so on and so on. Okay. So again, let's look at this really through this example first. So again, we're considering this sequence of functions f sub n, where f sub n of x is x to the n, defined on the closed interval 0, 1. And our goal is going to be that to show that this sequence converges pointwise on 0, 1. Now, what I have not said yet is what it converges to, right? We need a limit function in order to say this sequence of functions converges to this limit function in exactly the same way. When we had a sequence of real numbers, we needed to know what the limit was, right? I want to say this sequence of real numbers converges to L. I want to say this sequence of functions converges to F, okay? Now, let's sort of think about, right, what that has to be. And again, we've talked through this before, but it always helps to review. So if I fix an X value, right? That gives me a sequence of real numbers, okay? And if I look at that sequence, so that sequence is just going to be x to the n. And imagine the x value is fixed. Well, if that x value is 0, for example, then you just get 0 to the n, and that converges to 0. If that fixed x value is some, say, value close to 0, but not equal to 0, right? And I'm assuming it's in my domain, so it's larger than 0, but close to 0, then that number to the n is going to go to 0. Even if I go all the way up to, say, 0.99999, right? If I raise that to the nth power for higher and higher values of n, that's going to go to 0, right? And so, right, we know that since in this interval here, when x is between 0 and 1, and also when x is equal to 0, but not when it's equal to 1, if I raise that x value to higher and higher powers, the limit is going to be 0. The only place that will be different is when x is equal to 1. Because when x is equal to 1, this is a constant sequence, and it will just converge to the constant value 1. Okay, so we can sort of figure out here what our pointwise limit ought to be. And in a lot of ways, what we've done is we've sort of informally justified like why this is the pointwise limit. We might want to take a little more care, however, to actually write out a proof in just a bit. But before we do that, I want to also give you some sense of visually sort of what's going on. So you can imagine I could just plot, some of my sequence of functions. I could plot the whole sequence. Well, I can't plot the whole sequence. There are an infinite number of functions in there. But I sort of started, and so here's f sub 1, right? We know that's just x. Here's f sub 2, that's x squared. Here's f sub 5, that's x to the 5th. Here's x sub 10, right? Or sorry, f sub 10, that's x to the 10th. And here's f sub 20, right? So here's just some sort of representative functions that are in my sequence of functions here, right? And again, we sort of talked last time about the fact that you can sort of see that, that this sequence of functions is converging to between 0 and 1, everything is sort of flattening out, but then there's still this point up at 1 that's fixed, okay? Now, again, the notion of pointwise convergence, one way to think about it, right, is just come here, say come to point 2, and fix the value of x, or a, equal to 0.2. Now what happens? When I plug that into the function, what I get out is a real number, right? So when I plug 0.2 into f1, I just get 0.2 back out because f sub 1 of x is just x. When I plug in 0.2 to f sub 2, I get 0.2 squared, right? Which is 0.04. Right? And then I keep going, right? I plug in, so I can see that these values, right? My f sub n of a values are just the y values of these points. Those y values are converging to 0, right? Similarly, if I go over to 0.9, right? So over here at 0.9, here's f sub 1 of 0.9. Here's f sub 2 of 0.9. Here's f sub 5 of 0.9. I can see that these values, right, they're converging maybe at a different rate, but they're still converging to 0, right? So the y values of all these points seems to be converging to 0, okay? Now, again, if I sort of look at them side by side here, right, what I see is that at each fixed point, right, these sequences are converging, but they do happen to be converging sort of at different rates, right? Over here, sort of fairly close to 0, things are converging very quickly to 0. Over here, closer to 1, things are converging, well, a bit more slowly to 0, okay? At 1, at x is equal to 1, obviously, things are converging very quickly to 1, right? It's a constant sequence there, okay? So we get that for each fixed x value, fix an x value, then your sequence of f sub n of x is a sequence of real numbers that's converging to 0 here, as long as your x is between 0 and 1, including 0 but not 1. All right. So going back to this problem, right? We've looked at some pictures, we've made some sort of heuristic arguments about why this should be the case, but we now want to show that this sequence converges pointwise on 0, 1. Okay, so we want to write out a nice proof of this. All right. So in order to do this, it maybe isn't surprising, right? So we want to show that f sub n of x equals x to the n converges pointwise to the function f of x, which is defined to be 0 when x is between 0 and 1, including 0 but not 1, and 1 when x is equal to 1 on the interval 0, 1. All right. Now, for a couple of these values, the proof is just really, really simple, right? So, for example, if x is equal to 1, oh, so if x is equal to 1, then the limit as n goes to infinity of f sub n of 1, right, that's just going to be equal to the limit as n goes to infinity of 1 to the n, which is, of course, just going to be 1, which is, in fact, f of 1, right? All right. So when x is equal to 1, this is easy. If x is equal to 0, well, the limit as n goes to infinity of f sub n of 0 is going to be the limit as n goes to infinity of 0 to the n. Again, that's just always 0, so that's going to be equal to 0, which is f of 0. Okay, so far we see, right, that f sub n of 1 is converging to f of 1, f sub n of 0 is converging to f of 0, but we can't complete this proof simply by writing out all the possible x values, right? So at some point, we've got to sort of switch over and say, okay, I need to deal with these things a little more generally, right? Okay, so what if then x is between, I've dealt with 0, I've dealt with 1. What if x is between 0 and 1? Okay, well, now I want to show then we need to show that the limit as n goes to infinity of f sub n of x, which would just be equal to the limit as n goes to infinity of x to the n. I need to show that this is equal to 0 if I'm thinking about a fixed x value between 0 and 1. Okay. Now, how do I do that? Well, how do I prove that any sequence of real numbers, right? Imagine x is fixed. This is just a sequence of real numbers. I want to show that it converges to 0. Well, how do I do that? I'm basically going to do a mini sequence convergence proof within this proof. So what I'm going to do then is I'll choose, or sorry, I need to let epsilon greater than 0 be given. Now I need to figure out, I need to choose a natural number, capital N. Now I need to give some description of how I'm going to do that. Okay. But I want to choose this capital N such that I'm going to leave sort of a little space here to describe how I'm going to do that. Such that, and then I'll say, then whenever little n is greater than capital N, I want to show that x to the n minus 0, I want to show eventually that that's less than epsilon. Now, to figure out how I'm going to choose this capital N, I'm going to come over here to the side, give myself a little space here. I'm going to come over here to the side, I'm going to say, well, I want the absolute value of x to the n minus 0 to be less than epsilon. Okay. Now I can drop the absolute values because here x is between 0 and 1. So this is always positive. So I just want x to the n to be less than epsilon. I'm trying to figure out what condition do I need on n in order to make sure this is satisfied. Okay. Well, This is where you can pause it for a second, see if you could work through the algebra. There's a little algebraic trick here, but you could pause the video and see if you can find the capital N that will work for this. So if I look at this, one trick I think I'd like to play is I'd like to take the natural log of both sides. Now, natural log is an increasing function. So if I apply an increasing function to both sides of an inequality, the inequality still goes in the same direction. Okay. And if I do that, that allows me to play this trick that I can pull the n down, right? And so I get this. And now I have to be very careful here. I want to solve for n, okay? And so I'm going to divide both sides by natural log of x. So natural log of epsilon over natural log of x. Now, if we were not careful here, we'd go, okay, we're dividing by natural log of x, that's fine, keep the inequality the same way. But x is between 0 and 1. Between 0 and 1, natural log of x is negative. So you've actually divided by a negative number here. That's going to flip that inequality. So what we see here is like this ought to be, well, I put equals. Let me put approximately my capital N. Now, the issue here is that my N should be a natural number. Okay, so what I'm going to do is I'm going to say choose a natural number N such that that N is bigger than, that capital N is even bigger than this value. And so now, back in my proof, this was just sort of side work. Back in my proof, I now have claimed that this capital N will work. Let me show that will actually work. So whenever little n is greater than capital N, x sub n, okay, this will just be equal to x to the n. Okay. If I put, because x is between 0 and 1, if I put a smaller power, that will make the value larger. So again, n, capital N is smaller than little n. So I put a smaller power here, and because x is between 0 and 1, that will make this whole thing larger. Let me put an even smaller power than capital N. Let me put x to the ln of epsilon over ln of x. Okay. And now this is where you might be looking at this and going, oh goodness, what on earth is that? You can actually play some algebraic tricks here to make things work. But let me actually make this a little bit easier for you. If you recall, so this is a precise equals, the change of base formula for logarithms. This is actually just log base x of epsilon. Okay, so this thing sitting here is really just equal to x to the log base x of epsilon, which is epsilon. And so what we have demonstrated here is that for x is equal to 1, I can do this. For x is equal to 0, I can do this. For any x strictly between 0 and 1, I can do this, right? And so this is, in fact, the limit function. Okay. Now, before we erase this, I do want to note one important thing, and it's something we've observed already visually. If I look at my choice of capital N, my choice of capital N depends on x, right? If you look right down there in the denominator, my choice of capital N depends on x. And in particular, what we see is that as x gets closer and closer to 1, this is getting smaller and smaller, right? The denominator, right? So as x gets closer to 1, natural log of x is getting, in absolute value, smaller. And what it's doing is, in many cases, it's driving the size of this n larger and larger and larger. And we've seen that visually, right? As I get closer to 1, I have to go further and further out in my sequence to drive the values of my function down, right? So this choice of capital N is dependent on x, and it's dependent on x in ways we can't get rid of, right? There's just something inherent to this problem, to this sequence of functions that causes this to happen, right? It's not just some algebraic artifact. I can't get rid of it. Okay. Now, For now, you might go, okay, yeah, sure, whatever. We'll see actually that that's not true in every case. And in particular, it's not true in the next example that we'll look at. So in the second example, let's consider the sequence of functions f sub n defined on the whole real line by f sub n of x is equal to sine of nx divided by n squared. We want to show that this sequence converges pointwise on all of R. So here, our common domain is R, right? These functions are all defined for every real value of x you might plug in. And we want to show that this sequence of functions converges on all of R. Okay. So as I look at this, right, again, this notion of here that I'm gonna, maybe pick out individual x values, that's not gonna work, right? I need to show this works for every value of x. That's not gonna work. The other thing I need to figure out is what on earth I think this converges to. The only way I know how to show this converges to a function is to have a candidate for that function. So what I'd encourage you to do for a second is to maybe pause this video, maybe try to just think about it. Can you just look at this sequence of functions, maybe visualize on your own what's happening, and get an idea of what the limit might be. I would then encourage you to use some technology, use Desmos, use Maple, use MATLAB, Mathematics, whatever it may be that you like to use to visualize functions. And see if maybe you could use that to help you visualize this sequence of functions. So what I'd like you to do is pause the video, take a moment and see if you can come up with a candidate for the appropriate limit function. Great. So now if I look at this sequence of functions, one way to think about this, I think maybe the easiest way is to rewrite this as this. So I have this sine function. And it's oscillating between, the sine part here is just oscillating between -1 and 1. Its period here, as n increases, right? This coefficient is inversely proportional to the period. So as this n increases, the period gets smaller, right? So the sine function is sort of like it's getting horizontally compressed, right, by this factor of n. But then out front, you have this term that's affecting the amplitude. So even though this is always going between -1 and 1, now it's being multiplied by 1 over n squared. So it's bouncing between -1 over n squared and 1 over n squared. And as the n goes to infinity, this is going to 0. So you have these sine waves that are sort of getting compressed horizontally and vertically at the same time. Okay, so if you look at this, you might pretty quickly start to suspect that these are probably all just going to converge to 0. Okay, so let's see if we can prove that. We'd like to show that this sequence of functions converges uniformly to 0 on the entire real line. All right, so to prove this, we're going to start not this time with an epsilon, but with an x. Okay, so let x in the reals be fixed. Fix some particular x value. Okay. We want to show that the sequence f sub n of x, right, which is just going to be sine of nx over n squared. I want to show that this is equal to 0. Okay. Now, you might say, well, wait, isn't this just what you just said? Well, I've fixed an x now. So now that x is fixed, This is a sequence of real numbers, and I'm just going to treat x no longer like a variable, just like a fixed real number. Okay. All right. So if I want to show this, okay, then what do I do? Well, then I need an epsilon. Okay. So I'm going to let epsilon greater than 0 be given. And now I've got to somehow choose a natural number, capital N. Okay, how am I going to choose that? I don't know. Let's give ourselves a second. Okay. And then I want to say, well, then whenever little n is greater than capital N, I want to show that sine of nx over n squared minus 0, I want to show that's all less than epsilon. All right, great. So how do I make this happen? Well, let me come over here to the side. Right. Okay. I want eventually sine of nx divided by n squared to be less than epsilon. I'm imagining x is a fixed number, and now it's like I want to solve for n. Well, this is going to be a really nasty inequality to solve for n because I've got an n trapped in this sine function, and I've got an n squared in the denominator here. Now, I could ask myself, okay, which of those is more troubling in terms of trying to solve for n? It's really the n that's trapped in here, right? I'd need to use some sort of inverse sine function. I don't know. It's not something I want to do. Okay. So what I say is, well, okay, well, what else could I do with this? Well, what do I know about sine? And I'm sorry, I should say here, I should have absolute values here, right? Because I'm looking at eventually I want the absolute value of this to be less than epsilon. So the n squared I can take out of the absolute values because it's a natural number squared, which is always positive. This, though, I can't. So if I look at this, I know that sine of nx in absolute values, well, it's certainly always greater than or equal to 0, right? It's always less than or equal to 1, right, in absolute value. Sine bounces back and forth between -1 and 1, so in absolute value, the largest it could be is 1. And I could divide all this by n squared. Okay, so what I see is that this term over here is always less than or equal to 1 over n squared. So what if, instead of trying to get this thing less than epsilon, what if I focused on making 1 over n squared less than epsilon? If I did that, if 1 over n squared was always less than epsilon, then sine of nx in absolute values over n squared would also have to be less than epsilon, because sine of nx in absolute values over n squared is always less than or equal to 1 over n squared. So the idea is here, I'm going to substitute something that's a little bit larger than this. I'm going to make sure that that thing's always less than epsilon, then this will always be less than epsilon. Well, this is much easier to solve for n, right? So if I do just a little bit of work here, this will happen whenever n is greater than the square root of 1 over epsilon. Okay, and so the idea here is I'm going to choose my capital N to be a natural number such that that is always greater than the square root of 1 over epsilon. Okay, now let's see how that's going to work out for me now down here. All right, so this just ends up being the absolute value of sine of nx over n squared. Okay, this is always less than or equal to 1. Okay, now I can substitute something smaller in the denominator that will make everything larger. So something smaller than little n is capital N. And something smaller than capital N is square root of 1 over epsilon. And if I do a little bit of algebra, that's just equal to epsilon. So what have I shown here? I've shown that if you fix a value of x, I can always find a value of capital N such that whenever we go out past capital N in our sequence, right, our value sine of nx over n squared is always within epsilon of 0. Right? Okay. So I have in fact shown that the limit as n goes to infinity of f sub n of x is equal to 0. Now this worked for every x. in the reals, so we say that this series converges, sorry, this sequence of functions converges pointwise to 0, where here when we say 0, we mean the constant function 0. Okay, so sort of our concluding thing would be to say, so f sub n converges pointwise to f of x is equal to 0 on R. Okay. All right. Perfect. Now, let's contrast this with the previous example. In this example, if I look at my capital N, notice here that my capital N does not depend on x, right? The capital N that I pick here is totally independent of x. The same capital N will work for every x, okay? So in this case, it's almost as if, yes, this is converging pointwise, but in a way, it's almost as if there's some uniform rate at which everything is converging. It doesn't matter whether x is really big, really small, positive, negative. Everything sort of has to be happening at about the same time. I can go far enough out in my sequence of functions so that every x value satisfies this, right? Satisfies the condition, satisfies this condition here, right? So there's one value, capital N, here that would actually work for every x. So somehow what's happening here is a little bit different. And it's different enough that we actually want to give it its own definition. This is what we are going to call uniform convergence. So this sequence of functions does converge pointwise, but it converges even more nicely, and we call this type of convergence uniform convergence. So the next thing we want to do is formally define what we mean by uniform convergence. Now, while we will define this today, we'll only begin to scratch the surface of uniform convergence of sequences of functions, and we will continue our discussion of uniform convergence in later videos. So I will say that a sequence of functions, f sub n, converges uniformly to a function on some set A, if and only if for any epsilon greater than 0, there's a natural number n, so that whenever little n is greater than capital N, then this condition holds for every x. So the idea is you pick an n, and that n has to work for every x. The n can't change with x. The n must be independent of x. So you'll actually sometimes see this written as like n of epsilon. N can and almost always will depend on epsilon. It cannot depend on x, right? So the idea here is you need to be able to pick an n that does not depend on x in order for your sequence of functions to converge uniformly. Okay? Now, in order to revise our earlier proof to prove that that converges uniformly, the only thing you would do differently is get rid of the part at the beginning that says let x be a real number, because we don't want to fix x, right? So you would start your proof by just saying let epsilon greater than 0 be given. Okay, and then you show that you can do all of that stuff without worrying about what x is. It's totally independent of x. That's the notion of uniform convergence. Now, we will, in subsequent videos, work through some other proofs that something converges uniformly. So you'll see other examples, but you can very easily modify the previous proof to show that that sequence of functions does converge uniformly. So to sort of give you some sort of visual sense of what's going on, if we go back to that sequence of functions x to the n on 0, 1, the problem there is that if you fix your epsilon, right, no matter how small your epsilon is, there's always going to be some x values that you're not far enough, like your sequence of functions hasn't gotten down below there yet, right? So like here, you'll see that no matter what n you take, in this case, if you take n is equal to 20, then n is equal to 20. When n is equal to 20, f sub n of these points, right? For these x values, f sub 20 of those x values is not within epsilon of 0 yet, right? So non-uniform convergence is happening at vastly different rates. You have some places here where the convergence is very slow, even though everything else has already sort of gotten below some epsilon threshold. For uniform convergence, everything sort of has to be coming down at roughly the same speed. It's never going to be exact, but you think of it sort of orders of magnitude, right? Things over here are converging very, very slowly, whereas things over here are converging very, very quickly. For the sine of nx over n squared example, and I'll post a visual in Desmos that you can play around with as well, and you'll see that that whole sequence of functions sort of slides down at roughly the same pace, which is sort of the indicative behavior of uniform convergence. So going back to this, right, we see that this does converge pointwise on 0, 1. However, the convergence is not uniform. The rate of convergence depends on what x value you're at. X values very close to 0 converge very quickly. X values very close to 1 converge as slow as you would like, right? As you get closer and closer to 1, the convergence gets slower and slower and slower and slower. So it's really the fact that it's not just that there's some place where there's fast and some place where there's slow. It's that you can make the convergence as slow as you would like by getting closer and closer to 1, right? So however close you want your function to be getting to 0, you can go close enough to x that you can get your x value close enough to 1 that your function isn't quite within that epsilon tolerance yet. Okay. Now, again, we're going to continue to play around more with these notions of pointwise and uniform convergence. We will look at more examples, and we will start to examine what sorts of other characteristics might differentiate these. So, for example, if I have a sequence of functions that converges pointwise, right, is there anything nice that happens versus what if they converge uniformly? Now, the last thing I want to mention, and if this is not something you're totally familiar with, that's okay. We can think about pointwise convergence. So one way to sort of shorthand this is to say pointwise convergence says that, say, for every x in A and for every epsilon greater than 0. So this is, again, some sort of logic notation you may or may not have seen before. If you haven't seen it, don't worry about it. It's okay. For every x in A and for every epsilon greater than 0, there exists a natural number, capital N, such that whenever little n is greater than capital N, that implies that f sub n of x minus f of x is less than epsilon. Okay. Uniform convergence, we would abbreviate slightly different. So this says, for every x, you can do this thing, but it may depend on x, right? Because this n is chosen after the x is set, right? The n could depend on x. For uniform convergence, this says for every epsilon greater than 0, there exists a natural number n. Now here the natural number n is fixed before we ever say anything about x. And here what we want to say is that when little n is greater than capital N, then for every x in A, this condition must hold. Maybe it's gotten a little faint. It gets a little faint towards the edges. So you actually see here, you can see structurally in just sort of the logical definitions that these really are different. Now, you will almost never hear someone say this function converges pointwise and uniformly. Okay, and that's because uniform convergence implies pointwise convergence. And an interesting fact about this, if you've ever taken a course in mathematical logic, we teach a course at the undergraduate level, 2110, that does a lot of mathematical logic. You do proofs in a system, in a system of predicate calculus. And actually, this proof is not an analysis proof at all. It's really just a logic proof. It really just has to do with the structure of these quantifiers and where they're placed. So the fact that a uniformly convergent sequence of functions implies that it's also pointwise convergent. There's really no analysis to it. It's just sort of the way the definitions are structured that forces uniform convergence to imply pointwise convergence. That being said, you could certainly, write down a proof of this in sort of the standard way we do in analysis. But this is actually, I just want to emphasize that this is actually sort of true at a definitional level, at a structural level of how this definition is constructed. It has nothing to do with epsilons and n's, really. They're just sort of bystanders in what's going on here. So we'll stop here, and again, in future videos, we'll look at more examples and some of the consequences of each of these types of convergence.